Hello. Today we're going to talk about the beginnings of limits, how to define them, how to evaluate a limit graphically and numerically. So first, what a limit actually is. Now, the limit of a function is what we consider the y value of this function as you're approaching from a certain x value, both from left and right-hand sides. We will eventually talk about how to evaluate them only from the left or only from the right-hand sides. Now, again, when we're talking about limit, we're talking about approaching a number as we're getting closer and closer to that number. Now, one way to do this is to plug in x values to the left and right of it that are close to what you're looking for and see what number they approach. So, like, for example, if you want to evaluate this function, limit as x approaches 4 of x minus 4 over x squared minus 3x minus 4, one way to do that is to simply plug in 3.9, 3.99, 3.999, 4.001, 4.01, and 4.1. As you can see, as we're getting closer to 4, we'll be approaching some y value down here, from the right-hand side and from the left-hand side. And if both those numbers are agreeing upon the number they approach, that's the value of this limit. So that's what we're going to do in this exercise. We're going to plug in these 6 x values and see what we get. Okay, so we plug in 3.9 for x. The y value we get is 0.2040816 and a whole bunch of other numbers. So we'll just stick with 0.204. Plug in 3.99, we get 0.2004. Then 3.999, we get 0.20004. So as you can see from the left-hand side, we seem to be moving this 0, this 4 here, further and further to the right after the decimal point. Looks like the number we're approaching is kind of 0.2. Because as we have more and more zeros, the rest of the stuff here becomes almost irrelevant. Let's see if the right-hand side agrees. We'll plug in 4.1 in for x, and we get 0.196. So as long as this number is getting a little bit bigger and bigger, then what's going to agree upon this? So let's see what happens when I plug in 0.401. And I get 0.1996. And then when I plug in 4.001, I'm going to get 0.19996. So again, we're getting a little bit bigger, and we're approaching, getting very, very close to 0.2. So if I have a whole bunch of 9s, when that rounds up, these 9s will round to zeros, and eventually the 1 will round to a 2. So it seems to be approximately the value of 0.2. Which it actually is, we'll learn in a later date how to actually evaluate these things analytically. So that's certainly one option to do. It is very tedious, kind of annoying. Now, unless you have a computer program, then it becomes not that bad then. The computer does all the calculations for you. Just tell it what values for x to plug in and what kind of function you're dealing with. But if you're just doing this by hand, with a normal calculator, it's a little bit more challenging. That's why, for the most part, you're really not going to use this method to evaluate limits. Now, one really convenient way to evaluate limits is to use the graph. If you either graph it by hand or by a graphing calculator or have a graph to view, it is very easy at this point. You're just simply verifying what numbers they approach from left and right-hand sides. If it's approaching the same number, that is the value of the limit. Now, the downside to this method is not all questions will allow you to use a graphing calculator. For example, on the AP test, there are entire questions for multiple choice and for your response where you're not allowed to use a calculator at all. So you do need to know how to use other methods. But if you can use a calculator, this is generally a very quick and easy method to use. Now, before we get to some examples, there are some times when the limit does not exist. 3 different ways. First, if it's approaching different numbers from the right side as from the left-hand side. So in the example we just used, from the left-hand side it approaches 0.2, but what if from the right-hand side it approached 0.3? Totally different numbers, the limit does not exist in that case. This typically only really happens with piecewise functions. Any functions that are not a piecewise function, piecewise defined functions, they generally will be approaching the same number from left and right-hand sides. Unless we're dealing with a situation where the function increases or decreases without bound as x approaches its number. This will generally occur at the end of a function, when the function is just kind of going off to infinity, or at a vertical asymptote. That is another situation where the limit will not technically exist. Technically, in those cases, the limit approaches infinity, positive or negative, which is technically an answer, but also technically not a real number, so hence why we say it does not exist. Finally, if the function oscillates back and forth between two fixed values as x approaches the number. Oscillating functions are typically trig functions, and a normal trig function, which would just look like this, the normal sine or cosine function, is fine. It's when it looks more like this, they're kind of like slow, and then it like speeds up, crazy oscillations, and then go back to normal. Some functions will look like that, and we will see some examples like that later on. So first example, we want to evaluate the limit of this function on the graph as x approaches 3. So what I want to do is, here's 3 right here. And I want to go from the left-hand side of the graph until I get to 3, and then for the right-hand side. And if I meet at the same point, the limit will exist, and the y value at that particular point is our answer. So the limit of this function is 1. If they approach 2 different points, then the limit would not exist. So take a look at this answer. So they want to find the limit as x approaches 2. So again, here is 2 for the function. So we go along the graph, the left and right hand sides. Since the arrows meet at the same point, the limit is 2. Now, one important thing to note. The value of the function at 2 is not the same as the limit. The limit does not always equal the value. Sometimes it does. Like in this particular example, the value and the limit were both the same number. But if you'll notice, there's a hole on the function at that particular x value. Whenever there's a hole there, the limit and the value will not be the same number. The value of the function will be equivalent to the black dot. So here's our black dot. That means the value, f of 2, is equal to 0, the y value at the black dot. So you have to be careful. Make sure you're looking for what they want. If they want to find the limit, approach it on the graph from the left and right hand side until they meet at a single point. If you're looking for the value, look for the black dot or the actual value of the function. Like for example, f of 4 doesn't have a black dot, but we know it's right here, which is equal to 0. Okay? Take a look at this one. The limit as x approaches 2 of the absolute value of x minus 2 over x minus 2. So from the left-hand side, here's my function. I'm approaching this point. On the right-hand side, I'm approaching this point. As you can see, they're approaching 2 different values. Since they're not approaching the exact same number, we're approaching 1 from the right, negative 1 from the left. The limit does not exist, which we'll abbreviate as DNE. If you want to write out does not exist, that's perfectly fine. Abbreviating DNE is acceptable, at least in my class. Here we have our sine function. I want the limit as x approaches 1. So I go from the left-hand side all the way until I get to x equals 1. And from the right-hand side all the way until I get to x equals 1. They're approaching the same number, so the limit is 0. In this example, this is a better drawn example of an oscillating function. As you can see, we have no idea what's going on in here when x is 0. It's somewhere in this center point. We have no idea what's happening. Since we can't evaluate it because it's oscillating back and forth between 2 numbers, negative 1 and positive 1, this limit does not exist. Now finally, in this example, we're going to take a look at, we have one graph that's asking us many different questions. The value of the function and limits of the function. Remember, values of the function look for either the black dots or on the line itself at a certain point. If you're looking for the limit of a function, you need to approach it from the left and right hand sides on that graph. So f of 1, value, we're looking for a black dot. So when x equals 1, there's our black dot at 2. Now the limit, so we go along the function. We stop when we get to x equals 1. Go along the function, stop when x equals 1, and 2 different dots does not exist. So f of 4, again, value of the function. We're looking for a black dot. So we go to x equals 4, and I have a hole, but I have no black dots. There is no defined value of the function. So it also does not exist. But in this case, the limit does, because if I go from the left-hand side and the right-hand side, we're approaching the same number, which is also 2. So that's the difference between finding the values and finding the limits. Values, again, you're looking for a black dot or on the function itself. If there's no black dot, then it does not exist, or if it's on the function, then it does not exist. Limits are approaching the same number from left and right-hand sides. If they do, it exists and is whatever the y value is at that particular point. If they don't approach the same number, then they do not exist. Okay, so next time we're going to talk about how to actually evaluate these functions analytically using our algebra skills. So I will see you next time.